It's going to be a two-part presentation. The first part is going to be on design and sustainability, and the second part is going to be on construction. And it's the Arbour project. Sorry, I forgot the name of the project. I apologize for that. Phil Silverstein is an architect, a principal at Moriyama Teshima that's been with the company for over 20 years, and Olivia Keung is an architect there. Did I get your name correct there, the pronunciation?
Yeah.
Olivia. Excellent. Okay, I did something right. Okay, so I'm going to turn it over, and looking forward to the Q&A.
Great, thank you, Tom. Thank you, everyone, for joining us today. I'm going to start with a brief intro, and then I'm going to turn the table over to Olivia, who will describe the design and sustainable innovation, and then I'll jump back in to describe the structural innovation and the digital toolkit. So I don't want to take it for granted that anyone here in the conference knows who Moriyama Teshima is, so I'll give a brief intro to our firm. The firm was started over 60 years ago. In the late 1950s, Raymond started the firm. A few years later, he was joined by Teshima, and this project here is a shelter that's on a private golf course, which had a high level of detailing and a respect for nature, which formed the basis of our ethos. Soon after, we started the Ontario Science Centre, which was designed in the 1960s and brought words like hands-on and participatory, which were new and innovative concepts for a science center. The center was designed with respect to nature, respect to the trees and the tablelands in the valley, and it respected the vistas to the natural landscape, which were constant reminders that despite the emphasis on science and technology, nature is the basis of all life. We've had a chance to go back and revisit this project, and the initial vision of the respect for nature and integrating to nature is being realized. And these early projects form the enduring design principles of our practice, which is regeneration. We leave the site better than we found them, and generosity, which speaks to creating inclusive and social spaces, and generative, which is to find unique solutions to every project. And we try to bring this connection to nature to every project, even if it's like this one, which is the Saudi National Museum in Riyadh, which is a really simple reflection of light on the south facade in the desert. Or the Canadian Embassy in Tokyo, which has an angled roof, which is used to avoid casting shadows onto the adjacent imperial gardens to ensure the landscape receives the required light. And even in our interior spaces, such as the Multi-Faith Center at the University of Toronto, we try to connect nature through materials and spirit. And because we're a studio that's based in principle and not in style, we don't have one single leader. We have a community of leaders that are unified by the design principles of our ethos. And we like to throw this slide into presentations because when the Dalai Lama comes to visit one of your projects, you show that slide as often as possible. So I'm going to turn this over to Olivia now to describe the design and sustainable innovation of the Arbour.
Thank you, Phil, and thank you so much, everyone, for joining us today. You know, it feels like we're emerging out of a summer that was full of headlines about extreme weather conditions, whether it's heat waves in BC or wildfires across the country. And I think it's never been clearer that we're in the midst of a climate emergency today, and everything that we build has to address and acknowledge this. So when George Brown College opened up their international design competition for their Arbour, they were doing just this, envisioning what the building of the future should be. And from the beginning, there was a mandate for a tall mass timber building. And we wanted to give a shout out to all of the teams. This was the short list for the competition, because we're dealing with a level of innovation that makes it clear we won't get there alone, working in silos. And so all of these teams bring a wealth of expertise in terms of innovating and building mass timber buildings. We are partnered with Acton Austri Architects from Vancouver, who bring a wealth of experience in tall mass timber buildings. Beyond mass timber, George Brown also had a very strong sustainability mandate for an operational net zero carbon building, as well as future-proofing the building in terms of resilience and looking at future climates and integrating smart technologies in order to further this target. Next slide. So the Arbour is located in downtown Toronto on George Brown College's waterfront campus. And this context is important because there is a need for this building to really create strong connections to the public, and enhance and give back to the public realm that's right outside our doorstep. And so the heart of this building is a series of open collaborative student spaces that continue all the way up through 10 stories of the building and really knit together the verticality of the building. This location also gives us a really great opportunity to announce our strong sustainability mandate to the city in a very public way. So the ground floor consists of not only these student spaces, but also a childcare facility and a student fitness center as well. When we look at the landscape of tall mass timber buildings today, there's a growing number of projects going up around the world. Many of them are residential or commercial office buildings. So the Arbour is unique in that it's an institutional building and classified as an assembly building. And in this category, it will be one of the tallest in the world. This typology of building brings its own set of challenges. One of the main challenges is the need for spaces like this with a larger span. So gathering spaces, classrooms, lecture halls, and event spaces. And in a tall building, we want to be able to achieve this without resorting to the deeper beams that we normally see in mass timber structures. And so the structural solution that has been developed for the Arbour is a beamless solution. That's also a made in Canada solution. It's based on a module that will enable all of the big players in Canada to replicate this structure. And this is where the inspiration for our design began, understanding that mass timber structures are very dense structures. There was a desire to carve out of this a series of open, social, collaborative spaces for intense student activity that continues throughout the building. So if you go to the next slide, this is our learning landscape that really continues the sidewalk up through the building, up to the 3rd floor. Next slide. And continues up to an interconnected stair, and then up through the breathing rooms. Next slide, please. So the breathing rooms continue to the 9th floor of the building, and they sit against the solar chimneys, which are the vertical space that you see right outside the breathing rooms on the east and west side of the building. Next slide. The solar chimneys are central to our sustainability strategy, but they also signify the need to consider health and student wellness. And so all of these are broadcast in a very public way on the east and west sides of the building. Next slide. The solar chimney is our natural ventilation strategy. So it is required to rise up almost 2 stories above the main volume of the building in order to pull air through the stack effect. And then the mass timber structure dictates that we want quite a simple building form. And so what we're looking at is a design that's fully derived from the structural innovations as well as the sustainability features of the building. What this required was a very close collaboration process within the team. And the sustainability story for the Arbour is a story about how we use technology in order to collaborate and coordinate. Next slide. So we worked with a really fabulous team. We had Transolar, who was our sustainability consultant, and Integral Group, who was our lead mechanical and electrical design team. Next slide. So this shows our sustainability goals and innovations. So we're looking at a tall mass timber structure, so that addresses embodied carbon. We're also targeting operational net zero carbon, LEED Gold certification, and Toronto Green Standard Tier 4. So for those of you who are not familiar with the Toronto Green Standard, it's a tiered system that will basically mandate that by 2030, all new buildings in Toronto will have to be built to a net zero carbon performance level. And so the Arbour is setting a standard for all new buildings in Toronto 10 years ahead of its time. Next slide. So this slide shows our sustainability strategy. And we always look at our passive strategies first in order to drive down our total energy consumption before we start looking at our active systems. So our passive strategies include an excellent building envelope and high performance glazing, natural ventilation, and daylight harvesting. So the building will operate in passive mode for more than 35% of the year. So on a day like this during shoulder season, the HVAC systems in this building will pretty much not be on. Next slide. So this slide shows our active system. So when it gets a little bit hotter or cooler, our active systems kick on, and they are fueled by a district energy system and distributed through the building in a decentralized HVAC design. This shortens our runs and makes the system much more efficient. And you can see in the classroom section on the right side of this slide, our ventilation is being distributed through an underfloor air plenum, and heating and cooling happens through the radiant panels in the ceiling and distributed through heated or chilled water. Next slide. So how does a building like this come together? We have two rules of thumbs that I want to give you. First is that sustainability needs to be a topic of conversation from day one. It's very difficult to decide later on in the process that we want to design a zero carbon building. The second is that it requires intense collaboration and coordination within the team. So what we're looking at is an image of one of the breathing rooms, and I want to sort of dissect what's happening in this space so that you can appreciate why this level of coordination is required. The breathing rooms is one of the social interaction student spaces. So there's a large amount of exposed mass timber structure in this space. It also sits against our solar chimney. So you can see that outside the curtain wall on the right side of the slide. Our operable windows are open, so we know that it's operating in passive mode, and air is being drawn out through the windows and exhausted through the stack effect. The diagonal blades outside the curtain wall are sunshades, and they actually control the amount of daylighting and solar heat gain that's coming into this space. And finally, this is also an interconnected floor space. And so how fire behaves and how smoke travels has been heavily considered in this space. Logistically, what we're looking at is an image that has been modeled in Revit, and this is the same Revit model that we're using to produce our contract documents, and then rendered in Enscape. So everything that we're looking at, from the guardrails to the ceiling finishes to the mechanical and electrical systems, have been modeled down to a level of detail beyond what we normally see. So mechanical and electrical systems have been modeled down to a 1-inch conduit. These are softwares that we've been using for a long time. Many of us in the industry have already been using Revit for more than 10 years. But what was required on the Arbour was to really push this to its limits, and also to use Enscape not just as a rendering and visualization tool, but also as a coordination tool. So the next slide shows a series of diagrams that were developed for authorities at the city to understand how the solar chimney operates. And these diagrams were rendered in Enscape. So you can see the passive ventilation mode on the left side, and this shows the operable windows in the blue arrows in an open state, pulling air out and exhausting it through the louvers at the top, and then active cooling and heating mode on the right side. And these were important for everything at the city, from our alternative compliance application, understanding how smoke travels, even something as simple as calculating the GFA. It's not every day that the city receives a set of drawings with a solar chimney in it. Next slide. So another software that we had to really push to its limits was the energy model. And in a project like this, we use the energy model more as an iterative design tool in a very active way. And the design of the building envelope is sort of a good place for you to understand the level of coordination that's required. So our building envelope is doing a number of things for us. It's controlling heat loss, and in this design, we're targeting an effective R value of R35. It's also controlling the natural ventilation. Next slide. All of these factors also need to be weighed against the design of our prefabrication system. So prefabricated envelope is something that we often see in mass timber buildings because of the need to enclose the structure and protect the structure from moisture as quickly as possible. Next slide. So our goal is really to regularize the facade as much as possible and minimize our panel joints, because this is the weak point in terms of thermal heat loss. Next slide. And then finally, our envelope is also regulating daylighting. So in building science, we often learn as a rule of thumb that we want to reduce the window to wall ratio as much as possible. So it was a bit counterintuitive learning that in a high performing building like this, we've actually reduced the heating load so significantly that other loads start coming into play. And at a certain point, increasing our window to wall ratio in order to gain more daylighting gave us more meaningful energy savings. The other reason is that when we talk about sustainability, we also want to think a lot about the human experience, human health and well-being. And so we've actually created a space that's healthier for student learning. We know that daylighting is critical for student productivity and well-being. Next slide. So this shows our energy model results, and it sort of graphically shows this very clearly. The graph on the left side shows our total energy usage. So the bar on the left shows a standard building compared to the Arbour to the right of that. And you can see in the standard building, normally our heat load is by far the biggest load, but in the Arbour, we've driven that down so significantly that now we're challenged with the daylighting and plug loads. Next slide. This shows the targets that are mandated by the Toronto Green Standard Tier 4, and you can see that the Arbour actually exceeds these targets. So we have our total energy use intensity at the top, our TEDI target in the center, which basically describes the efficiency of our building envelope, and the greenhouse gas emissions, which describes both the efficiency of the building as well as our fuel source. So the Arbour is an all-electric building, and here in Ontario, we're blessed with a very clean electric grid. So you can see our GHG index is pretty close to 0. Next slide. So all of this is even more amazing because the Arbour is located on a tight urban site. And in the landscape of zero carbon buildings, we've only begun looking at this typology, but we know that the majority of the world today lives in urbanized environments. And so if we're going to really make a dent in our fight against climate change, this typology is really critical for us to get a better understanding of. So now I'm going to pass it to Phil to speak to the other side of the carbon equation, which is materials and structural innovation.
Thank you so much, Olivia. There's so much that we're proud of in terms of sustainability and innovation. Even the prefab facade alone is something new to North America, definitely new to us. But one aspect that I'm going to touch on is the mass timber and the structural innovation. First, I'll describe the gravity system and the main structural system of the building, and then get into the structural testing program that we use to validate the main flat slab system. So the building, this is an image provided to us from our structural engineers, Fast and Ep, and it's a really simple system. A bit of a hybrid system. We have concrete caissons that go down to bedrock, concrete foundation walls and ground floor slab and feature stair. But then rising up from there is a steel lateral core, post and beam and diagonal bracing, and then fully mass timber system right up to the roof panels. So during the competition, one of the things we're faced with is trying to develop a system that could be used for across the board by all building typologies, from assembly, residential, commercial, what have you. But we're really looking at a flat slab system that didn't have deep beams like you see in this image right here, because we didn't want to sacrifice ceiling height. We did want to span 30 feet or 9 meters. So there are many ways to do that. What you're looking at here is an image supplied to us by Fast and Ep, our structural engineers. And this is the most economical way to span 30 feet. However, that is not what the solution we're looking for at the Arbour. What we ended up developing is a unbelievably brilliant system in conjunction with ourselves, Acton Austri, and Fast and Ep. We've developed a system that's diagrammatically shown here, starting with the columns. The columns are 430 millimeters by almost 1,200 millimeters, so they kind of act like walls. And for that reason, we've called them wallums. It's not the greatest name, but we're kind of stuck with it. Spanning between the wallums are these long 9 meter, beyond 9 meter slab bands. And these are composite panels. It's a 7-ply CLT system with a composite concrete, 150 miller thick topping. And then in between that, we have these infill panels, which are also 7-ply. So you can see in the middle of this image here, there's a red section. And I'm just going to highlight that red section there. You can see how unbelievably thin this system is. This is beyond a 9-meter span. And you can see that the extension below the main infill panel is only 150 or 6 inches below the main span. And here I've just highlighted the exact component that I'm talking about, are these long slab bands. When we get to a column connection, there's just 2 cores through the slab band. It allows us to connect from column to column. And then what we do is infill with concrete around the steel post for fire rating. So I'll just walk you through the simple floor plate. Like we mentioned, it's a 9.2 meter span, 9.2 by 7.2. And that allows us to have this huge, wide, column-free space that allows us to program this any way we wish, from large classrooms to small classrooms or offices. And it also future-proofs it so for any kind of future tenant that could move in. So the north side and the south side of the building are a 9.2 meter clear span space. So we start with going up three levels at a time of a steel post and beam and diagonal braced lateral core. And then we infill that core with 7-ply CLT slabs. The wallums then go in at a regular grid. And then around the perimeter, we have tie-back panels, followed by these 9-meter slab bands. We also call these slab bands, the other term I may be using is TCC, which is timber concrete composite panel. These panels, it's about 2 days to install per floor, and then another 2 days to install the infill panels. Once these are installed, we then follow up with an acoustic mat and a 50 millimeter acoustic topping. So the innovative part of this system is that slab band that I described before. And the project received funding from Natural Resources Canada. And what we developed is a comprehensive test program designed to investigate the parameters for different types of composite connectors and the CLT reinforcing. And we're looking to determine which system is the most simple to install, which one has the lowest cost and most efficient TTC system. And the goals of the testing program were to determine the out of plane shear capacity between the wood and the concrete, the properties of various shear connectors, and the ultimate capacity of the slab bands or TTC panels. And to achieve these goals, we actually conducted 60 tests. These are all actually made public, and the results of the test verify what we actually implemented into the design. So going back to this section here, I've highlighted the slab band. You can see what I've highlighted here are the shear reinforcing screws. So these reinforcing screws connect all 7 plies of the panel. And then compositely connected, we have, because we need to connect the concrete to the timber, are composite connectors. Prior to testing, the industry didn't have enough specific information available as to how the various composite connectors would behave in a CLT panel and how the varied embedments would work. So we looked at 3 different types of connectors. Now the top here shows the 45-degree angled screw connectors. The middle image is are steel plates, and then the bottom one is a proprietary system. It's an HPV plate. Here's an image in Prince George, Alberta, where the testing was done, University of British Columbia, and this shows the angled screw composite connectors. This is an image showing the steel plates and the trees grater like HPV plate. So this image here shows the full scale of all the tests that were conducted, 16 total. We had 18 small tests that were conducted to investigate the shear capacity and the stiffness and failure mechanisms of the TTC system. The half-size tests, all 30 of them, were done, consisted of CLT panels with no concrete topping. And we tested the unreinforced, half-reinforced, and fully reinforced. And then there were 12 tests, full-scale tests, to test the 3 different types of TCC connectors that I described in the previous slides. This is a drawing showing the three different types of samples that were created for the large scale samples. At the top, we have the screw connectors, the steel plate connectors in the middle, and the HPV connectors. The steel plate embedment was tested at three different depths, at 35 millimeters, 70, and 90. And this image shows the large scale sample that was tested. This shows the screw connectors and the reinforcing of the concrete. So the concrete was set, the test was brought in. You can see on the left here, there's a section of the wallum on the left and the right. There's this 9-meter span. You can see the 7-ply slab band with the concrete topping, and this was tested to failure out of shear plane. So the conclusions of the test were that the small scale tests validated our initial assumptions that 35 millimeters embedment was sufficient for the TTC slab bands, and that screw reinforcing greatly increased the shear capacity of the panels. And the addition of the 150 millimeter topping compositely connected to the CLT panel significantly improved the out of shear capacity by over 167% when compared to a raw CLT panel. And lastly, the slab band with steel curve plates exhibited the highest capacity and stiffness, and they were priced by multiple suppliers to be the most economical option. So the results and finding of this proved that the steel curve plate had the highest capacity, had the best stiffness, and was the most cost effective. And that's exactly what we incorporated into our design. So those tests are made available. It's now a system that, now that it's gone through the natural resources testing, this is a system that it's validated and it can be used on any project worldwide. So with all the structural innovation, sustainable innovation that this project went through, it took quite an extensive digital toolkit. A lot of these tools were some of them were new to us, some we'd been using for a long time, but we've re-envisioned how we use these tools in our office and how we work with consultant teams that are spread from coast to coast throughout Canada and the US. So I'll break this down, the tools that we use, by talking about the construction drawings and then the tools we use during construction coordination. So at the beginning of the project, when we're in the competition mode, we relied heavily on SketchUp. All of our modeling was done in SketchUp, and renders were sent out to Doug and Wolf for rendering. But we quickly migrated into the Revit world because, like Olivia said, we had such a high level of coordination that needed to be done. And actually, like Patrick said when he gave his from Element 5, the level of coordination has to be done very early on in a project because this timber is being cut and cored, and penetrations are being made in the factory. It's not being done on site. In fact, we don't want to make any cuts or core anything on site if it can be avoided. You started using Enscape as a 3D visualization tool, primarily for in-house understanding of the spaces, but also for client review. And our structural engineers use a program called Modelo for their 3D visualization of the timber structure. We did use AutoCAD, not as extensive as we had in the past, but it was done for some offhand studies. But the one tool that we used that was really transformative for our office was the Autodesk BIM 360 document management. Like I said, we had consultants from Vancouver, Ottawa, Toronto, spread out all over the country, New York. We all needed to be connected in the cloud. So our model is hosted in the cloud, and everyone connected, which allowed us to do drawing reviews in the cloud and allowed for file storage. We use BIM 360 Insight for drawing tracking and issuances. We also started utilizing Bluebeam Studio far more extensively. We would load the current drawing set into and create a Bluebeam Studio session that allowed live simultaneous drawing review and coordination. Our structural engineers use Delubal RFM to determine the composite outcomes through the timber testing program, and IESV was used for energy modeling. So the image on the left here was actually supplied during, or we created this during the competition, and this was created in SketchUp, like I said earlier. Doug and Wolf created the rendering from our SketchUp model, but this is a very time-sensitive proposition. weeks can go by to get a rendering like this. So when we switched into Revit and added the Enscape plugin, it allowed us to create images on the right, which take literally seconds to generate. Now, there's a lot that goes in the background, don't get me wrong, but once that work is done, like adding in the people and adding in tables and even paper, pens on the tables, you can generate these very fast renders that really enhance the discussion that we have in-house with consultants and with our clients. It also allows us to do real fly-throughs and animations of the project that are quite realistic. So we have a pair of VR goggles, actually multiple pairs in our office, that the design team puts these goggles on, and we can stand at the top of these learning landscape or in the breathing rooms and look down over the balconies, understand what kind of views we're looking at, how the sun affects the space at different times of day. And in the image on the left, this is the Tallwood Institute at the top of the building. We were able to play around with the proportion and scale of the skylights, the number of skylights, and how the sun affects the building, how the daylight comes in at different times of the day, season to season. And for really the first time ever, when you're immersed in that space, you can, you normally wouldn't be able to realize this until the project's built. But here we are during design, fully understanding the impact of nature on the building. Our structural engineers had a similar experience with Modelo. They used this program for 3D visualization. I should mention another shout out to our structural engineers, Fast and Ep. They brought a lot of software to us for us to better understand the system. There's so much intricacies with this hybrid system. You can see the steel here is quite significant in the solar chimneys, that a 3D visualization tool like this helps us all understand what we're looking at. So during construction, a lot of the same tools were being used. Revit clearly we're using for change management. And we continue to use Enscape as a 3D visualization tool. Olivia mentioned that we created those sections of the solar chimneys to help the authorities understand exactly how smoke travels through the system during active and passive mode. But we really rely on Revit heavily for the coordination of elements like mechanical and electrical systems and the penetrations that are required. The constructors on the project are PCL, the Toronto office of PCL. And PCL are using the BIM 360 document management for package staging. So when we issue a change, that isn't contractually realized yet until a change order is issued. So the full drawings that get issued with a change get loaded into the package staging platform in BIM 360. And then when a change order is issued, it moves up the ladder into the current set. They're using, PCL is using BIM 360 glue, and they use this to combine all the trade drawings. From Nordic Structures is supplying the timber, Walter Steel for the steel, and then mechanical, electrical, everything is brought in to BIM 360 glue, and then migrated into Navisworks, where we conduct our clash detection. So Primavera is the scheduling software that PCL is using. And a really interesting thing that they've done is they've taken the Primavera schedule and the Revit model and combined it together into a program called Synchro for 4D sequencing. So this allows us to jump on a call. Usually we do this weekly, and they show us a different sequence of how the timber's coming into play, and it allows our consultants to understand in about a minute and a half exactly how they're going to sequence it and how long each sequence takes, and maybe something that could be out of sync that we think is necessary to, for instance, create a diaphragm, like when to install that steel angle around the perimeter. We're also using Bluebeam Studio. Previously during design, we'd use Bluebeam for our drawing reviews. But now when we receive a large submittal that has multiple consultants that have to review it, like the timber, for instance, that requires pretty much every consultant to analyze it, we'll open up a Bluebeam session, drop the shop drawings in, and together we all simultaneously review that shop drawing. It really helps cut down time when you normally would have to pass the drawings back and forth from consultant to consultant and do that round robin review. We're using Onware. This is new to our office. Onware is a contract administration software that puts our entire effort in the cloud. So on site, we can be reviewing shop drawings responding to RFIs, issuing changes, all in the cloud, wherever we are. And our consultants all have access to this. And this has been a big eye-opener for us. It brings everyone under the same page, from our project managers, our clients, our consultants. We're all looking at the exact same information. We're using River for internal team communication, and we're also using Microsoft Teams for that reason. But Microsoft Teams is really has been wonderful for project team communication. But one thing that we're very proud of on this project, that PCL is being instrumental in bringing forward, is the paperless process. So there's no paper on site. Maybe a few sticky notes. We'll definitely have a permit set stamped on site, but aside from that, the guys laying rebar will have a tablet on site. I'll be on site with a tablet. We'll all have tablets, and we'll all be connected to the BIM 360 portal, all looking at the exact same current set. This is a screenshot that I captured from a review last week. This is from CADWorks 3D. I got permission from Nordic, who are the mass timber suppliers and installers, to use this. This is our shop drawing. So once a week we group up, and we can fly around through this 3D shop drawing model. We also have a backup 2D print of this, so that anything that comes out of the 3D review, we can translate that into the 2D set and then load it back up or return it back to PCL. Just last week, there was this one area that there was a corner where two angles weren't quite meeting at the same plane, and it would be impossible to understand that in the 2D mode. So being able to open up CADWorks and view it in 3D allowed us to see something that normally we would never have known until it was actually constructed. So last, I'm going to play a video for you. This is Synchro. This is what happens when you take the Primavera scheduling software and combine it with Revit. It's not the most exciting. If this was on TikTok, it may only get 3 likes, but for me, this is fascinating. For the first time ever, I can understand exactly what's happening on site in a visualization format that even the owner can see and understand. So this is the learning landscape and the timber that's being installed around the learning landscape. You can see the large 3-story column with tiebacks. Those tiebacks will stay in place until it's adequately secured in place with enough bracing around it and tie-in beams. You can see the slab bands have the concrete topping installed on it. They come installed with topping. And once the columns are capped, we can remove the tiebacks. And the column on the far left that's about to be installed is the largest column on the project. It's a 630 millimeter by 1720 millimeter. That's 2 foot by 5.5 foot mega column. This whole process you're looking at here is about a 2-week process, start to finish, including the concrete topping.
So amazing presentation. Thank you so much. We're just kind of bumping up on the edge of our time here.
That was the end of my presentation. So thank you very much. I
absolutely love the 4D animation there from PCL. I think that's, if it was on TikTok, I would like it if I was on TikTok, but I'm not. But yeah, I mean, it's just so many amazing innovations that your team developed for this project. And I love the fact that all that information is available for other architects around the world to learn from. And super proud of this work that's being accomplished in Toronto, Canada. So congratulations on an amazing project. I think that hybrid beam system is super innovative. It's going to enable mass timber to be used on these commercial real estate institutional projects. So yeah, amazing work. Congratulations on that. Just, I mean, a high level question before we have to jump, but this was a competition project. So your team put together a competition, obviously. Was the use of mass timber driven by the client, or was that an initiative that you guys developed to meet the requirements of the project?
It was client driven. So all of the competition teams that you saw were developing different mass timber structures.
And the other innovations related to sustainability, like I don't know if this is a passive house project or a LEED But obviously, this solar chimney is super innovative. All these things were developed by your firm, or were these sort of requirements that the owner demanded be incorporated, like the meeting certain sustainability targets?
I think meeting Tier 4 of the Toronto Green Standards was something that was decided on from the very beginning, and I think the full team, our design team as well as the client team, worked together very on to develop a project charter. So deciding what we want to target very early on, and then just making sure that we stick to that throughout the project.
Yeah, great. Well, amazing presentation. One of the best that I've seen really in all the presentations we've done over the years. Very detailed. I love the fact that you shared all the different technology that was in use over the course of the project. Congratulations to everyone involved with the project. Amazing work, and please keep it up and come back and share your next one with us. And with that, I think we got to wrap up and get into our next presentation.
Thank you very much.
Yeah, thanks
For having us.